Hi, my name is Spencer Strauss, and I'm the Director of Engineering at Dimensional Control Systems based out of Troy, Michigan. And the topic I'm going to cover today is all about dimensional engineering and the field that is dimensional engineering. The simplest definition I can give you for what dimensional engineering is it's the study of how part-level imperfections can affect the product design requirements at the assembly level. So there were a few different things that I just said in that single sentence definition, so we're going to rewind a little bit and talk about what some of those are. The first thing we're going to talk about is what are assembly level design requirements and where do they come from? Well, the assembly level design requirements are dictated by the actual design team. So the design team tells us, be it they're an aesthetic requirement or a performance requirement, that their overall assembly must meet, and that's our overall target for the dimensional engineering task. So what causes us to possibly miss that target is those part-level variations. And where do those come from? Well, those are typically dictated from an engineering drawing, be it GD&T or organic tolerances, but those numbers are actually coming from the manufacturing process that is used to create the part. And again, that's going to come from the drawings or maybe some historical knowledge of the process that's being used to create the part. The next topic I'm going to talk about is just all about collaboration. And this is, when you're a dimensional engineer, how do we influence design, how do we influence manufacturing, and how do we influence the actual metrology of the parts once they're manufactured? So I like to think of dimensional engineers as the engineers who are a little bit in the middle of everything. And by that I mean, at the design phase, we are influencing locators. We're understanding those design requirements, and we're having feedback back and forth with designers to talk about what we could do differently, what we could do better. When we get to the manufacturing phase, we're letting the manufacturers know, hey, these are the critical features for our model. If you can, make sure we are reducing the variation on those features, then, maybe we'll meet our design requirements more often at the assembly level. And then lastly, for metrology, we can tell the metrologists where the parts should actually be measured at. If an entire face has a profile tolerance on it, then there will be a temptation to check the entire face. But odds are we don't need to know about the entire face, and the dimensional engineer can highlight where the actual critical locations of the face are, and by doing that, you might be able to reduce the overall scrap rate of the parts, because now you're measuring more towards part function and not towards just the actual drawing. And lastly, also in the metrology area, once we actually have that measured data, we can reroute that data to an analysis tool and see where our model actually is performing at. And as tool wear occurs, we can determine if we can continue accepting these parts or if we should maybe, change our methodology around a little bit. All right, so now you know what dimensional engineering is, so what would be an example of a dimensional engineering project that you might partake on? So the example that I love to use is the example of a motor and stator. And let's say that the critical gap for my design is between the motor and the stator. So the design team provides us with the dimensional requirements for this gap and how the parts are located to each other. Perhaps at that phase we have a few back and forths, but overall we take what they're doing. Then we take those requirements and go to manufacturing and we say, given the processes that you plan to use to manufacture these parts, how much variation do you anticipate for these key features? You can then take that, create a drawing, add the actual model-based definition into it, and then we can go to manufacturing, and manufacturing can provide us with what the anticipated variation is for those important features based on the processes that they plan to use. We can then take that, go to an engineering drawing, we could add the actual MBD to the part file, and then we can move on to the next part, which would be right before production. So using the assumptions that we've gotten from manufacturing and the design requirements, we can actually create potentially a three-dimensional model for our tolerance analysis to see how we anticipate it performing. If it's performing well, we can move on to metrology. If not, maybe we have to hop back to the design and let them know how to do a few things differently. We can then move on to metrology and once again tell metrology where to measure, but in addition to that, as tool wear happens in the manufacturing side, metrology is going to catch that, and the dimensional engineer can determine, is this tool wear something we need to be worried about and address, or is the variation in my parts still acceptable? If I'm still meeting my design requirements, I don't need to address this tool wear. We are still good. We don't need to actually reject those parts. Now that we've talked a little bit about what dimensional engineering is and given an example of that, I wanted to talk about a quick success story that I have for a dimensional engineering project. There was a medical device company that was creating a frame that was about 300 millimeters in length. The idea of this was that it had 9 LEDs on it in specific locations, and these 9 LEDs needed to be within a very tight range of plus or minus 0.45 millimeters, relative to the nominal coordinate system of the assembly. Now, initially, the results looked great using the baseline numbers for what manufacturing told us they were going to be able to manufacture each of these parts relative to. Now, once they actually started manufacturing the parts, they were a little bit further off of those goals, and when they were further off, we were no longer meeting that plus or minus 0.45 requirement. So what we did as dimensional engineers is we changed up the datum scheme a little bit. We played around with the locators. We didn't necessarily tighten any tolerances, but by doing that, we were able to bring those results back within the plus or minus 0.45 range. And when they went to continue on manufacturing it, they didn't run into any further problems until, tool wear dictated again that the dimensional engineer had to step in. And that's the role of the dimensional engineer, staying involved from design to manufacturing to metrology and, again, beyond. So the next thing I wanted to talk to you guys about today is how dimensional engineering is being implemented, at different companies in industry. There are really 2 different approaches that we see to dimensional engineering, probably more, but I'm going to boil it down to just 2. The first way is the subject matter expert route. And this means that you perhaps have either one identified dimensional engineer, or you have a group of dimensional engineers who are aware of the field and understand all of these different things that I've spoken about so far. The second way that it's being implemented is just as another task for the design engineers to make sure that they are doing. Make sure that you understand all of these fundamentals of dimensional engineering and incorporate that to your design process. There are pros and cons to both these approaches. The pro of the dimensional engineering route is that the dimensional engineer really understands all the fundamentals, but they might not understand the product as well. So there'd have to be more communication between them and the design team. Now, with the other route, where the design engineers and mechanical engineers are in charge of this process, it requires them to have a deep understanding of dimensional engineering throughout, and that can be a difficult skill to learn while also doing all the other tasks you're asked to do as a design engineer. However, you have the benefit of really understanding your product and really understanding the design requirements, so if you can implement it in that way, you might have some additional knowledge that the dimensional engineer does not when they're the only one worrying about this concept. All right, the last thing I wanted to talk about today is just the future of dimensional engineering. The future of dimensional engineering, I see a few different things that I hope will be implemented soon and common across the board. The first one is tolerance optimization. And when I say that, I mean that a lot of companies are using legacy tolerances. On last year's prints, for example, this fender had a profile of 3 in this location. So we're going to go ahead and use a profile of 3 on this year because last year worked. Well, maybe it only worked because the supplier who's creating it is actually manufacturing that to a profile of 1, and we should really be controlling it on our drawing to that as well because our design requires it. On the contrary, maybe we can actually loosen that up and manufacture the part for cheaper. If we open that profile tolerance up from 3 to, say, 5, now that part is that much easier for our supplier to produce, and maybe we gain some leverage and we can cheapen the overall product cost. The other big thing that I want to see implemented into the dimensional engineering process is the idea of closed loop. And I mentioned this a little bit earlier when I talked about how we can take the metrology data and put it back into a 3D model to really better understand how these part level imperfections are contributing to my final assembly level requirements. And really closing that loop is something that a few companies are really working hard to achieve. And I'm hoping that within the next 5 to 10 years, we're going to see that commonality across the board, where you have metrology really working closely with manufacturing, really working closely with design, with the dimensional engineer working, again, closely with all three of those, so that that loop is closed and those different silos are no longer quite as separate. So, in summary, the dimensional engineer is really the center of the entire design, manufacturing, and metrology process. The dimensional engineer brings all of these different fields together and oversees the design, the manufacturing, and the metrology to not just say, hey, this part is in spec, or hey, I can design this part to this level tolerance, and hey, I need my final assembly to meet this design requirement. The dimensional engineer actually takes all of that information and combines it into one and sees how these different departments interact with each other and tries to, again, act as an explainer almost between all three of them, so that we aren't just individually understanding how parts are measured or how parts are made or what the requirement is. Essentially, the primary role of the dimensional engineer is to act as the conduit between the design, the manufacturing, and metrology.